Again, my name is Ziyad Hanna. I'm the Senior VP of R&D at the Jasper Design Automation. I'm going to talk about how to expand the reach of formal powered by our coverage techniques. So basically, Jasper provides a large set of applications called Jasper apps, Jasper Gold apps that span over several areas of the front end, including formal property verification, SOC integration, and IP development and verification. So this is we have a large set of capabilities here. I'm going to focus in my talk on the coverage. Okay. So Jasper is a mature private company providing several solutions in the design verification domain to various customers, and we have here a snapshot of some of the customers that are allowed to show and to share their logos. There are a bunch of them. We have over 30 customers, big customers in the domain, and so basically the company is that has a presence in the R&D in 4 places. The headquarters in Mountain View. We have R&D offices in Israel, Brazil, and Sweden. We have more than 70 people in the R&D focusing on advancing the technology frontier, and basically it's a very high investment on the technology side for advancing the company roadmap. Technology Advisory Board, we have a list of technologists across the world, from Oxford, Rice, Princeton, and so on and so forth. Basically, Jasper is investing in the academy and external front as well. So now back to the solutions. As I mentioned, we have several applications in the domain of property synthesis, security path verification, equivalent checking, post-recon debug, and low power, which is rising concern everywhere, and architectural modeling. But for now, I want to focus on the design coverage verification. Basically, it's a big concern to know how comprehensive is my verification, what coverage I achieved, and involving several techniques in simulation, formal verification, and other techniques. So the idea how to measure the contribution of formal, in particular, in the presence of the whole techniques, and how in the interoperability of the coverage with other techniques, and how to collect these things into unified database like UCDB or UCIS, and how to measure the coverage holes in formal, etc. So basically, coverage is a big concern to accelerate the overall verification closure process. And as formal, informal specifically, there is different techniques, and we are focusing on what we call coverage models and coverage items, as I'm going to describe in the coming slides. If I want to summarize what are the big concerns in coverage in general with the communication of formal, basically what you call stimuli coverage. This is the first one. I want to know how restrictive is my design behavior under the formal setup. What did code and where did code exist and generated in the design? So I want to know how restrictive my environment I'm doing under constraint, over constraining my design, and such. The other concern in the coverage is about the completeness of the coverage. Okay, I want to know how complete my coverage sets, property sets. Do I compute all the design behaviors? So how many properties I put there? I did put enough properties, or I need to add more properties to measure the completeness. Another big concern is about if I have a set of properties that I managed to prove, those are proven properties that are valid. That means they managed to search the entire search space and get to the approved. The question: what coverage I achieved by the proven properties? Okay, this is a big concern. Probably I have managed to prove the properties, but they are not meaning that much. I want to know their contribution to the overall coverage. Another concern which we are trying to answer in our technique is bound-proof coverage. Formal is capacity of formal is increasing over the years, which is able to handle big designs right now. but we still face situations where we have bounded proofs. That means we manage to run the property into that number of cycles or bounds. So what's the coverage of bound proof? Okay, assume I get a bound of 55 or let's say 100 of that property, but I don't have a convergence or full proof. What does it mean? Is it enough? Is that bound is enough? If not, how I want to improve the other bound? How I want to get a full proof based on this coverage, analysis, and debug? So basically, are the 4 questions that are concerning the formal flow that we try to address in this. Now, in connection to simulation, basically we have design the test, the test bench. There is a simulator running there with API, driving and reading, writing and reading to the coverage database. I mentioned UCDB as an example, but we want to take this into formal as well. We read that design the test into Jasper Gold coverage app and extract from there what we call coverage model. And we read from the coverage database through the API the list of unreachable cover items or cover targets and try to see if they are coverable on the RTL using the formal technique. Basically, the fact that we identify unreachable cover targets and prove them then can reduce the denominator when you are measuring the overall coverage. So in the other way, we can when we have the coverage model inside the formal analysis, we can hit some covers that are not reachable or uncoverable, so to speak, in the simulation domain and basically improve the overall coverage. So this kind of two-way communication with coverage database gives us great interoperability with simulation and formal, and the idea to have the collaborative measurement and integration of the coverage to increase the confidence on the DOT. Now for some technical aspects of our technique, basically when you ask a question, what kind of coverage model you do and you create in such a tool. So basically we build what we call cover items, which is implicit or explicit functional events of the RTL of the design D. So basically given an RTL, we identify a set of cover items. And this collection of these sets, we call them cover items. This is CIE.D. And the coverage analysis, we try to identify their status from the formal techniques by trying to run them formally and see for each cover items if they are coverable or reachable or not reachable. At the end, we want to know what's the percentage of these cover items, how much we managed to trigger in simulation or formal of the design end. So basically, the main thing here is the coverage model. Now, for stimuli coverage, for example, we identify the subsets which are reachable under the environment, or unreachable under the environment, or unresolved or bounded proof under the environment. And the overall coverage item is the union of all these cover sets. So basically, given an RTL, we identify the set of cover items and try to identify their status from reachability point of view. So this is the coverage model. Now for completeness coverage, we want to know for each property P, okay, under environment E of design D, what are the set of cover items in the cone of influence that are part of the coverage model, basically intersection of the coverage model with the cone of influence of the property. And for each property, we identify that set and union all these subsets from the coverage model to create the cover points that are relative to the whole properties, and thus we can achieve what we call the completeness of the coverage. To illustrate that, basically, if you think about a set of properties, we identify each property P0, P1, P2, etc., their cone of influence, and we collect all the cover items that are intersect with this cone of influence of the properties, and all the cover items that are outside the cone of influence of the properties that are not measured or not covered by the properties, that are not part of the coverage that contributed by the properties. We go one level beyond, down. If given a property and we can identify from the cone of influence what is the what we call proof core. Proof core is a subset of the cone of influence of the property that is contributing really to the validity of the property. So basically, this example, we have a Verilog block there, and the property is if you are in stage 2, you implies stage 3. So basically, for proving this property, we don't need the entire cone of influence of the property. That means some of it will be outside what we call proof core. That means the contribution essentially contributed to this to the coverage is on the proof core. In this case, we have state 1, 2, 3 are the main contributors of this property. That means that the outside COI is not that important. So if you go through the structural analysis and collect the COIs that are in the cover items in the COI, all of them basically are optimistic measurement. With the proof core, you will have more precise measurement to understand the contribution of the property validity out of the overall design. Basically, this is kind of saying that in wording here, basically, we have to give them a set of properties, and we identify the cover items based on the coverage model that I described before, and either it could be behavioral properties coming from the user or extracted automatically in the design. We collect the proof core per each property and union of all the cores together, and the overall contribution of the properties is the set of cover items inside the proof core from each property. So basically, this is a subset of the union of the COI, the cone of influence of all of them. So this is a precise analysis. To achieve this analysis, we leverage the formal engines to be able to delineate the proof core from the COI of each property. This will give us a precise coverage measurement. Coverage basically, it's the coverage app that we have in the Jasper provides a set of capabilities besides the analysis to collect or to compute the coverage model. For time being is branch coverage, statement coverage, and fault coverage. So the app produces set of reports, either textual reports or GUI-based reports, or Jasper database of the coverage. And we have a set of queries to extract whatever queries needed to know, for example, how many cover items or what are the cover items that are outside the proof core of the sales property, or what are the set of cover items that are contributed as being triggered with the bound less than the property bound, and so on and so forth. Basically, we give you the whole flexibility to extract and debug the results of the coverage app. So bottom line, user can correctly determine the efficiency of their formal test bench based on the coverage analysis here. And this is an evolving front. And for debugging techniques, for example, if you have a cover item which is not reachable, that indicates some unreachable code. The question how to debug it, why this cover item is not reachable. So you're leveraging what you call just the visualize capability. We'll be able to analyze, to understand why this cover item is not reachable. The tool, so basically the tool is equipped by a comprehensive GUI interface to show you the COI that is in the context. It provides a hierarchical report per block and to show you how many cover items being covered and or reachable or not reachable inside every hierarchy. The GUI highlights the code of influence in the code itself directly on the source code. You can choose the set of what reports you would like to see, for example, out of COI, inside the COI, inside the proof core, and so on and so forth. And the tool generates comprehensive XML and or textual format, and this is saved into database that can be queried in a more comprehensive way when you see the whole data being created from the tool. So for bounded proof, basically things are there more comprehensive because In bounding proof, we want to know out of the set of cover items that are relevant to the property, if it's not converging, want to know what cover items exceeded the property bound, which one are below the property bound, and which one are reachable, etc. And an immediate conclusion could be when a situation that the property, let's say the property managed to get to bound 50, but all the cover items that are intersect with the property, all their bound is, let's say, below 50, let's say 30. That means the property managed to exercise all the interesting cover items with the property and even beyond. That means the bound 50 looks kind of reasonable or good. It's not guaranteed that this is foolproof, but at least from confidence, from debuggability, understanding if the bound is sufficient or not, this is give you a more coverage to understand the behavior of the property and their bounds. And in the source code, you can see the certain cover items with their bound. For example, here you see in the right-hand side that the tag right deck, it managed to get to the 31. So basically, tag the bounds for each property on the source code, so the user can see the COI and see what events being triggered and to what level. As far as case studies, basically coverage app is being used by several customers, and one customer is doing DB engineering on ARM-based CPU peripheral. Has several blocks there in the design, including sensor controller, clock and reset management blocks. Engineers were moderately familiar with formal, not that much, but they know a little. The process was to use the coverage app to eliminate all the dead code and work toward 100% code coverage goal. Used the app to confirm there was no over-constraining by analyzing the stimuli coverage reports and make sure that the stimuli coverage is not that relaxed or not that tight. It's just tries to that verification block. Leverage data from bound proof to increase the coverage of the bounds of the properties in the formal analysis. So the benefits of them, as they stated, they were able to quickly meet the objectives of the project from the coverage closer specification. They're very satisfied with the coverage app underlying formal analysis, where they're in some properties you managed to have exhaustive proofs, and some of them got bound proofs, and combining them together with the coverage, they increase their understanding and their confidence in the design. The same team managed to get unreachable cover targets from the simulation database and use it inside as it proof targets in Jasper coverage goal and the coverage app, and managed to find some of them unreachable, and that means reduce the load from the simulation environment to try to achieve these coverage goals. So in the future, this basically Jasper and formal technology will continue to expand, and by providing more and more solution to more complex design in the emerging domain of SOC and IP development. We'll continue to push the formal to more limits and expand the applicability of formal for the users. And basically, we're driven by ROI. So Jasper formal solutions will continue expanding. We have more than 30 big customers now and keep increasing to leverage the ROI and the benefits of the tool. So what will be mean to you someday, basically, will be default choice for almost every verification task in the RTL and even above. We have various capabilities to apply for certain problems to be solved using under the hood capabilities with Jasper apps. The tool will guide the process and the usability to get to the maximum benefits of the technologies. And overall, the idea is to improve the productivity of the engineers in the validation in general and the design.
There's any questions in Bristol?
Yeah.
We have one question in Bristol from Julia.
I'm trying to kind of understand the whole process. And my question is, how exactly you decide that your coverage item inside your cone of influence, does it mean that your coverage items defined as in a kind of formal language. Is that correct?
Yes, the coverage items can be specified by the user using the SVA or PSL language, and we extract coverage item automatically based on the coverage model. Coverage model, I mentioned, we support four coverage models for the time being, including statement coverage and branching and the toggles. Toggle coverage. Basically, the user can expand the coverage model as needed, and the coverage model will create the set of coverage items as the baseline for measurement.
Okay, thank you. Okay, thank you very much. Thanks, Ziyad.